Hello, today we're going to talk about rate laws. Remember that a scientific law is something that summarizes the relationship between variables, okay? So it summarizes the results of many experiments. It doesn't attempt to explain it. So in kinetics, we write rate laws, which describe how the concentrations of the reactants affect the speed of the overall reaction. So a rate law is going to typically look like this, where you say rate is equal to, and then we have something called the rate constant, which is represented by lowercase k for the rate constant. Now, then you will have one or two or three different reactants. I'm going to use just two of them right now. And then those reactants will have an exponent. Sometimes that exponent is 0, sometimes it's 1, sometimes it's 2, 3, 4. Whatever that exponent is will give the order of the reaction in relation to that specific substance. So the way I have this written, the reaction is 0 order in respect to A and first order in respect to B. Then you would add those exponents to find the overall order for the reaction. So this one is first order overall. Now sometimes we just don't even write when it's 0 order, we just don't write the species at all. Now, let's try a different one. So if we have A squared and B cubed, okay, if those are your exponents, then you would have second order in terms of A, third order in terms of B, and fifth order overall. So those are rate laws. And the way this is written now, basically the concentration squared, the concentration of A squared times the concentration of B cubed times some constant will give us the rate of the reaction. So it gives us the relationship there as A changes by a certain amount and B changes by a certain amount. How does that affect the speed of your reaction? So let's talk a little bit more about that K, the rate constant K. So K is always lowercase k, and the unit of K depends on the order of the overall reaction. So I'm going to say, I'm going to make a little table here to help you out. So the order, let's say it's 0 order, then the units for K. Now I'm going to use molarity as my unit for amount and seconds as my unit for time. You can replace molarity with any amount unit depending on the reaction that you're doing. Or you can replace S with any time unit, like minutes or hours, depending on what the reaction is being measured in. But I'm going to use molarity in second to explain this. So the order, when K, for 0 order reaction, the unit for K is just molarity per second. So molarity and per second. I'm going to use negative exponents to denote when it's on the bottom of a fraction. I've been doing molarity per second like this, but this will make it much easier to see the pattern. Right? And so a possible rate law for this would be just, rate equals K times that substance to the 0 power. Now again, we don't even have to write the 0, just rate equals K. So that's why your unit for K is similar to a unit for rate, where it's a concentration over time. Now if you have a first order reaction, so the rate law is something like rate equals K, A to the first. The unit for K is just seconds negative 1. The molarity cancels out because you have a molarity per second in your rate, a molarity here, so molarity cancels and you're left with just per seconds, so inverse seconds. If you have a second order reaction, your unit will be molarity negative 1, S negative 1, okay, and your rate law could look something like this. Or you could have two separate things where they're each first order, leading to an overall second order. So because you have molarity being used twice, that's how you wind up with molarity on the bottom now in your unit. So one of the molarities gets canceled out completely and the other one is now on the bottom. Now it's just going to follow a pattern from there. Third order is going to be m-2, s-1. And it will look something like this, or you could have multiple different things adding up to 3. And fourth order would be m-3, s-1. So you can see s is always on the bottom, s is always -1, but molarity is dependent on the order. So the 0 order will have molarity on the top. The first order molarity is completely canceled out, and then second, third, fourth, etc. You'll just keep adding one more molarity on the bottom, or one smaller negative exponent. So those rate laws are determined experimentally. Okay, we can't just look at the reaction and figure out the rate law. We have to do experiments. So one thing that they'll have you do on the AP exam is look at data from example experiments. And they'll give you the experiment number or the trial number. So trial 1, trial 2, trial 3. And then they'll give you the concentration of a substance, the concentration of the other substance, and then the rate. And there might be 3 substances, but there might be just 2, and that's fine. So for example, I'm going to do a really simple one. So let's say the rate is 2 molarity per second. My original molarity of A is 0.5. My original molarity of B is 1.0. In the second experiment, I do my rate of A is 1, and my rate of B is also 1, and now my rate is 4 molarity per second. And then in my third experiment, my concentration of A is 0.5, and my concentration of B is 2, and my rate is now 8. Okay, so your strategy here is you need to find the order of the reaction in respect to A. So you want to pick 2 experiments where B stays the same. So I'm going to use experiments 1 and 2. And then you will look at the change in the concentration of the substance. Okay, so the change of A is times 2. 0.5 times 2 is 1. So that's the change in A. You also look at the change in rate. The change in rate is also times 2. Okay, so to figure out then the order or the exponent, you would say, okay, what exponent makes that true? And x must be 1 in order to make that true. And that's how you find the order. Now let's do B. So for B, we want to pick 2 reactions where A stays the same. So I'm going to pick 1 and 3 because A is 0.5 in both of those. Now for B, we go from 0.1 to 2. So it changes by a factor of 2. The rate changes from 2 to 8. So the rate changes by a factor of 4. So to find out the order of the reaction, I need to find out what exponent makes that true. And so that exponent would be 2. So 2 squared is 4. So that would be a very simple set of data to be able to figure out the order of the reaction for A is first, the order of the reaction for B is second, and then the overall rate would be third order. Okay, so once you figure out the order in respect to different substances, they could ask you a couple follow-up questions. They could ask you to write out the rate law, which will be something like this: rate equals K, A to the first power, B to the second power. You can write the one in, but you don't need to. The other thing they could ask you to find is the actual value of the rate constant K. So what you do is just pick an experiment. It doesn't matter which one. I'm going to use the first one. So you plug in the rate, 2 molarity per second. Let me go ahead and write it in like that with exponents to make it a little easier for you guys to see. We don't know K, but we know A in that first experiment is 0.5 molar. And we know that B is 1.0 molar, and that's squared. Because it's squared, I'm going to just write it like this, again, just so you guys can see it better. All right. So can you see that there's 3 molarities here? 3 molarities. So when I'm going to divide to get K by itself, so 0.5 times 1 times 1 is just 0.5. So 2 divided by 0.5 is 4. Okay. But we need to think about our unit as well. So right now we have molarity times s negative 1. So the s negative 1 stays the same because we're not affecting seconds at all when we're dividing by these 3. So s negative 1 stays the same. But you have a molarity and you're dividing by 3 more molarities. So one of them will cancel out and you're left with 2 of them in your final unit for K. Okay, now you could figure that out each time if you wanted to, or you could go back and look at the data table we made for the different units of K. Now, because this is a third order reaction overall, we know that the exponent for the molarity must be negative 2. And so that is the follow-up question that they very frequently ask when you're doing this type of problem. Okay, so here's another example. We want to find the rate orders for both of the reactants, and then that'll help us find the rate law for the overall reaction. So to find for the CO, I need to pick 2 reactions where NO3 stays the same. So I'm going to use 2 and 3. I'm actually going to compare 3 to 2 because 3 is smaller, and I don't like fractions. So if I go from experiment 3 to experiment 2, that's 4 times larger. Okay, 4 times larger in terms of the concentration. And then if I look at experiment 3 compared to experiment 2, it is also 4 times larger. So to make this equal with a particular exponent there, x must be 1. So the order in respect to CO is 1. Let's do NO3. So we want to pick 2 reactions where the CO stays the same. So I'm going to pick experiment 1 and 2. Again, I'm going to compare 2 to 1 so that we're comparing the smaller one to the bigger one. And in this case, it's twice as big. And if we're comparing experiment 2 to experiment 1, be careful with your exponents. Okay, and you can use a calculator, but if you divide that, you'll also see that that's times 2. Right? So what exponent makes those the same? An exponent of 1. So it is first order in respect to NO3. Now we need to write that as an overall rate law. You always write rate equals K. And then we have CO to the first power and NO3 to the first power. And again, you don't have to write the ones, but you can. Now to find the value of K with units, we're going to plug in the rate. So I'm going to use the first one, 1.68 times 10 to the negative 2. And that's molarity per second. And then K is what we're looking for. CO for that experiment is 1.20 molar. Oops. And NO3 is 0.720 molar. And so when I divide and solve for K, I get 0.194. And when we are dividing with units, so one of the molarities will cancel out, but the other molarity will wind up on the bottom, or negative 1, which makes sense because it's second order overall, so you will have a negative 1 as your molarity exponent for the unit of K. Let's do one more example. Let's find for A. I want to use experiments 1 and 3 because the B stays the same. So A, you get 3 times bigger in terms of concentration, and the rate gets 9 times bigger. So the exponent that makes that true is 2. So A must be second order. Now, if I want to find out the order for B, I want to pick 2 reactions where A is constant, so I'll pick experiments 1 and 2. B doubles, and the rate also doubles. So what exponent makes that relationship true? And that's an exponent of 1. So it's first order in respect to B. So the rate law is rate equals K, A2, B1. Now I want you to notice the order is 2 that doesn't matter with the coefficients in your reaction. The overall reaction is just 1A reacts with 1B to produce 2C. So the order of the reaction is an experimental thing, right? And that will relate to the speed of the reaction. That has to do with all of those factors that we talked about with collision theory, the orientation and the activation energy. So it does not necessarily relate to the coefficients in that balanced chemical reaction.